So let's start off by taking a look at the parametric equations of a line that we spent last lecture sort of deriving. So consider the line that has the parametric equations x equals 5 minus 2t and y equals 1 plus t. Now we were able to use this last time to detect whether or not points were on the line. Like if I gave the point 1, 7, I could tell that this is not on the line because I would just plug in these two equations. 1 equals 5 minus 2t, 7 equals 1 plus t, and I would check what values were needed to make each one of these things happy. For example, the top equation needs t to be 2, the bottom equation needs t to be 6. And since the same value of t doesn't work for both, this point's not on the line. On the other hand, if we were to look at the point minus 1, 4, then we'd find that this is on the line because we'd set the two equations x equals 5 minus 2t, y equals 1 plus t, and we'd find that the first equation is solvable for t equals 3, and the second equation solves for t equals 3. And so that would tell us that the point minus 1, 4 would be on this line. But here's something we didn't do last time that's just as useful. Rather than just test points for being on the line, we could generate them by plugging in values of t. For example, if we were to plug in t equals 0, we would get 5 minus 0 and y equals 1 plus 0. So we would get the point 5, 1 when we plugged in t equals 0. If we plugged in t equals 1, then we'd get x is equal to 5 minus 2, or 3, and y is equal to 1 plus 1. And so we would have this point at t equals 1. If we plugged in t equals 2, we would have 5 minus 4, or 1, as the x value, and we'd have 1 plus 2, or 3, as the y value, when t is equal to 2. And we actually already saw that this value right here corresponds to t equals 3. And if we sort of keep plugging in, we can find the values at t equals negative 1 and t equals negative 2. We could even plug in fractional values if we wanted to. If we plugged in t equals 1/2, we would get x is equal to 5 minus 1, which is 4, and y is equal to 1 plus 1/2, which is 3/2. And so we would have the point 4, 1.5 right here. Now if we put all of these points together, we're going to get a line, which isn't terribly surprising. In fact, we knew that this was the equation of a line. In fact, it's the equation of a line who passes through the point 5, 1, right there, and it's parallel to the vector minus 2, 1. The vector minus 2, 1 is this vector right here, and clearly this line's parallel to it. And that's not what I want to draw your attention to. What I want to draw your attention to is this idea right here. For any value of t, there is one and only one point on this line connected to it. That sounds an awful lot like a function. We could think of t as an input value. And then we could think of x and y as a pair of output values. And so what we have is we would have a function whose input value are real numbers t, but whose output value are x's and y's. Let's formalize this idea and revisit this example. If f is a function with inputs from a set x and outputs from a set y, we write f colon x arrow y, which is read f is a function from x to y. Now all of Calculus 1 has studied functions who looked like this. Functions from r to r. You would plug in a real number and you would get a real number out. But what it looks like is that these parametric equations are describing a different kind of function. They're describing a function whose inputs were real numbers, but whose outputs were ordered pairs, elements in R2. And so a lot of times we write a little arrow over the top to indicate that the output values are in R2, that they're not scalars, that they're, if you'd like, points or vectors. And we call objects like this functions whose input value are real, but whose output values come in R2 or R3. And I'm just going to write this as Rn. These guys are called vector-valued functions because their values, what they spit out, aren't scalars. They're in Rn anymore. And there's a way we visualize a vector-valued function. Let's consider the vector-valued function defined by L of t equals the vector 5 minus 2t and 1 plus t. If you think about it, we're describing x-coordinates and y-coordinates. So this is just the same line we were looking at, x equals 5 minus 2t and y equals 1 plus t, but we're just changing our perspective. Instead of thinking this as some generic equations of a line, we're thinking of it as a special kind of function. Now, how might we graph a function like this? Well, if we were to plug in an input value, say input value 0, t equals 0, then the output value would be the vector 5, 1. So we'd have a vector who looks something like this. I'll put some tick marks on. And we'd have a vector who looks like this when t is equal to 0. This would be the vector L of 0. L of 1 would be the vector 5 minus 2, comma 1 plus 1. Sorry, I was having a brain fart there. So that would be the vector 3, 2. And so we would have this vector right here. Here's L of 1. At L of 2, we would have the vector 1, 3. And at L of 3, we'd have the vector minus 1, 4. And so the picture's pretty similar to what we had last time. So for every value of t, there's a corresponding vector that we could look at right here. The only problem with trying to represent the picture like this is it's really, really complicated. You've got vectors all over the place. You have to index them at every single point. And this is me just drawing a small collection of them. If we were to draw every possible vector, it would look something like this. And it would just get almost impossible to read. But there is a slightly different way to look at this thing. Rather than drawing all of the vectors at the same time, let's draw them sequentially. Let's draw them one at a time for each value of t. For example, did you get the impression of an arrow moving forward in time? In fact, that's one of the reasons why we select this as the letter for the input variable, is intuitively, we think of a vector-valued function as a function of time. You give me an instant of time, and then the output will be a position vector, an arrow who is pointing at a specific point in the plane right here. Now, that gives me a nice way of visualizing a vector-valued function as sort of this arrow moving in time, and we're seeing the animation snapshots for each value of time. But that's still hard to draw the picture. So another way of visualizing a vector-valued function is to imagine that we'll keep track of a little red dot at the end of the position arrow, and we'll drag that dot around as we move the vector. So let me try this one more time. By dragging the point, we see that we've traced the exact same line segment we had before. We recovered the equation of the line with a little bit of a flow to it, a directionality. As a result, vector-valued functions are sometimes called parametric curves. And the shape they trace out as we let that position vector move forward in time is called a plane curve if it's in R2, and a space curve if it's in R3. Let's try this out on another example. Plot the plane curve given by c of t equals cosine t sine t. So remember, the idea of this is we're going to go and start plugging in values of t, thinking of them as time, and we're going to sort of see the position vector, where the position vector is pointing, and then we're going to try to imagine that position vector flowing forward in time. So let's start off at time equals 0. So at time equals 0, we'll have that c of 0 is equal to the cosine of 0 times the sine of 0, which in this case is the vector 1, 0. So we'll have a vector, I'll put some tick marks on here, and I'll just put my tick marks 1 unit away all around. We'll have this right here is the vector c of 0. And so we'll mark this one point right here. We could try to plug in c of 1 next, see what happens sort of 1 unit of time later, but that would require me knowing what the cosine and the sine of 1 radian is, and I'm not really that good at that. So let me sort of work my way up through the next couple of time increments that would make sense right here. Let's see, what would be a good one? How about pi over 4? That would get me cosine of pi over 4, sine of pi over 4. Cosine of pi over 4 is 1 over root 2, which is about 0.7 on both of these pieces. So there would be the vector c of pi over 4 and the corresponding dot in the plane that it's pointing to. So we went from 0 to pi over 4. Well, let's just double that increment of t again. Let's go and see what happens at pi over 2. Well, at pi over 2, we're going to get the cosine of pi over 2, which is 0, and the sine of pi over 2, which is 1. That means we'll get this point, this vector and point right here. In practice, if you were doing this on paper, you couldn't keep drawing and erasing these arrows over and over again. So we sometimes use another convention to help us figure these things, to help us plot these things on paper. And that convention is to simply mark the time values that we got these points. So instead of drawing the 3 arrows like I was doing before, I could instead mark this like so, in order to figure out what's going on right here. This allows me to go and at least plot more points kind of quickly. For example, if we were to go and plot, say, c of, what would be the next one, 3 pi over 4. We're going to get the cosine of 3 pi over 4, which, since it's in quadrant 2, would be negative 0.7, roughly. And the sine of 3 pi over 4, that's 45 degrees quadrant 2 for sine, which is positive 0.7. And we would get this point right here, at time equals 3 pi over 4. And you can start plotting your way through. At time equals pi, we'll get this point. At time equals 3 pi over 2, we'll get this point. At time equals 2 pi, we're going to end up right back where we started, since cosine of 2 pi and sine of 2 pi are the same. And in fact, we're going to just trace this pattern going from t equals 0 to t equals pi over 4 to this dot, 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 and simply repeat this over and over and over again. This would suggest that the plane curve is a circle of radius 1 centered at the origin who's spinning around counterclockwise. Now, that was just sort of based on lots and lots of pictures. Is there any way that we could check this out? Well, it turns out that there is a way of analyzing the shape of that curve without having to plot through all of the points. Let's reconsider this example here. The vector-valued function L of t equals 5 minus 2t, comma 1 plus t. If we were to write these things down back in their parametric form, x equals 5 minus 2t and y equals 1 plus t, we have these two equations with this common parameter. Well, imagine we were to solve both of these equations for the value t right now. So if we solved the first equation for t, we would end up with, let's see, we would have x minus 5 is equal to minus 2t, or x minus 5 divided by minus 2 is equal to t. On the other hand, we could solve the second equation for y. We would get y minus 1 is equal to t. But since these two t's have to be the same thing, it's the same input value, we could set these two equations equal to each other. That gives us x minus 5 over negative 2 is equal to y minus 1. So if we were to multiply through, we have x minus 5 is equal to negative 2y minus minus 2, or x plus 2y is equal to 7. So this is the equation of a line in the plane. Moreover, when y is equal to 0, it says that x is equal to 7, so the x-intercept has to be at 7, which we know to be true. And if x is equal to 0, then it says that y has to be 7 over 2, or 3.5. Well, we know that to be the y-intercept. And so this is indeed the xy equation of this curve right here. Again, remember how we said that this is sometimes called a plane curve? Well, this is sometimes called the equation of that plane curve. So let's go back to our circle example. And let's try to do the same thing. Let's write down parametric equations for this. In other words, the x-coordinate is given by the cosine of t, this part, and the y-coordinate is given by the sine of t. So let's solve these two equations for t and set them equal to each other. If we solve the first equation for t, we're going to get that that t is equal to the arc cosine of x. But now that I know what the t value is, I could just plug that directly into the second equation. And I'll get y is equal to the sine of the arc cosine of x. Now for those of you who came out of Calc 2, you should remember that trig of arctrig always simplifies if we draw the correct right triangle. So let me do a quick little bit of work right here. Let's let theta be the angle called the arc cosine of x. So I'll draw a quick triangle right here. There's the angle theta. X is the adjacent over the hypotenuse. So the Pythagorean theorem says that the missing side is the hypotenuse squared minus the adjacent side squared. So now that I know the triangle that corresponds to theta, and this entire bit right here is just the angle theta, y is going to be the sine of theta. So y is going to be the opposite side, the square root of 1 minus x squared, over the hypotenuse, which is 1. And so that gives me an equation that has x's and y's in it. Now remember that arc cosine only gives you values in quadrants 1 and 2, and if we were to look at what this equation is, this equation only says that y can be positive, so it's somehow describing the top half of this curve, which intuitively speaking is in quadrants 1 and 2. However, if we square both sides of this equation, we get y squared is equal to 1 minus x squared, or x squared plus y squared is equal to 1. And this right here is exactly the equation of a circle of radius 1. So it turns out we did plot our curve correctly. This process is sometimes called eliminating the parameter, solving for the parameter in one of our equations so that we can substitute it into the other equation and have an equation that has just x's and y's. Find a vector-valued function with the plane curve given by the ellipse x over 2 quantity squared plus y over 3 quantity squared equals 1. And in case you don't quite remember how conics work, whenever you have an equation like this, x over a number squared plus y over a number squared equals 1, that's an ellipse who intersects the x-axis 2 units away, since that's the bottom number in the x, and who intercepts the y-axis plus or minus 3 units away, since that's the bottom number right there. Oops, not y, 3. So how might we do this? This problem seems like it's the reverse of the other ones. The other ones, I gave you a function, had you sketch the curve. Now what I'm doing is I'm giving you a curve, and I'm asking whether or not you can find a function who traces this out. This is sometimes called a parametrization problem. Can you parameterize this curve? Can you find a vector-valued function who traces it out? Where might we even start on something like this? Well, we could start with the last example. The last example gave us a function who traced out a perfect circle. The curve c of t equals cosine of t, sine of t. Unfortunately, this isn't going to give me an ellipse right here because, well, no matter what value you plug in for t, cosine of t always stays between 1 and minus 1. Here, on this ellipse, we're going to need x values that at least hit the value of 2 and minus 2. In fact, they're going to hit every x value in between here. That might give us an idea. Maybe what we could do is we could multiply the x value by 2. So 2 cosine of t is now a value that will at least hit plus and minus 2. Well, the same thing, the y value can only go between 1 and minus 1 if it's sine. I needed to get all the way up here to 3 and minus 3. So we might multiply this thing through by a positive 3. Would that work? Well, one of the things we could do is we could try plotting a couple of points. At time equals 0, we're going to get 2 cosine 0 sine of 0, which is this point right here. At time equals pi over 2, we're going to get this value up top. At time equals pi, we'll hit this value. At time equals 3 pi over 2, we'll hit this value. And then at time equals 2 pi, we'll cycle all over again. So at least through these 4 points, we're going to cycle over and over and over. We could also go one step further and do what we did last time. If we want to see whether or not we get exactly this curve, we can try to eliminate parameters. So what we'll do is we'll take this and we'll turn it into two equations and two equations and one unknown. X equals 2 cosine t, and y equals 3 sine t. So if I solve, let's try the second equation this time. If we solve the second equation for t, we're going to get y over 3 is equal to the sine of t, or t is equal to the arcsine of y over 3. Now that I have a t value, I can plug that into the top equation. That will get me x is equal to 2 times the cosine of the arcsine of y over 3. Now that's a trig of arc-trig problem. So I'll go and I'll draw an angle who represents arcsine of 3. Sine is opposite over hypotenuse. That means that the missing side has to be the hypotenuse squared minus the opposite side squared. And now I want the cosine of this angle. And so the cosine of this angle is going to be the adjacent side over the hypotenuse. Now this equation right here only has x's and y's, but it doesn't look an awful lot like the original equation. But let me multiply both sides through, say, by 3 halves. So I'm going to have 3 halves x is equal to the square root of 9 minus y squared. And then I'll square both sides. That will get me 9x squared over 4 is equal to 9 minus y squared. And then let me divide everything through by a 9. So I'm going to multiply both sides of this equation by a 1/9. And if I do that, I'm going to find x squared over 4 is equal to, let's distribute this 1/9 through. We'll get 1 minus y squared over 9. And if I rearrange that, that's x squared over 2 squared plus y squared over 3 squared is equal to 1. And that's exactly the equation we started off with. So this will work. However, it's not the only one who does. You might instead say, well, since sine and cosine both wobble back and forth, why don't we swap them? Why don't we make this 2 times the sine of t and 3 times the cosine of t? Would that work? Well, we could do a first test by simply plotting points. At t equals 0, we're going to get this top point right here. At t equals pi over 2, we're going to get this point right over here. At t equals pi, we're going to get this point. At t equals 3 pi over 2, we're going to get this point. And at t equals 2 pi, we're going to get back to this point. So at least it looks as though we're tracing the appropriate points in at least the corner points. You could go through and check that this in fact does work. So the point of this example is it shows you that there's more than one way to parameterize a curve. You can have 2 different vector-valued functions who still give you the same plane curve. For example, if we return back to this line one more time, we already saw that the line traced by this is the equation x plus 2y equals 7. Imagine we were to take the equation of this line and say solve it for y. So we'd have 2y is equal to negative x plus 7, or y is equal to negative 1/2 x plus 7 halves, just distributing that 1/2 through. If I were to make the equation x equals t, well, then this equation right here would just become y is equal to minus 1/2 t plus 7 halves. And this would give me a different parametric equation for the line. So I could build an entirely brand new function here. I could build the new vector-valued function v of t is equal to t, comma, minus 1/2 t plus 7 halves. I already know it's going to trace out the same curve, but it's going to trace out the curve in a different way than the previous one did. If I plug in time equals 0, I'm going to get this point. If I plug in time equals 1, I'm going to get this point. And time equals 2, time equals 3, time equals 4, time equals 5. And so in this case, I'm tracing this line from left to right rather than right to left, which was the original tracing. So given a curve, we can always find a function who parameterizes it, and we can usually find more than one. Let's try another example. Plot the vector-valued function h of t equals cosine t, sine t, t. Now, This is actually going to be pretty hard right here, because our ability to draw in R3 is pretty restrictive. We could try plugging in individual points right here. For example, if we were to plug in t equals 0, we would get the point, let's see, h of 0 would be cosine of 0, sine of 0, 0. So this first point would be pointing at a point 1 unit along the x-axis, no units along the y-axis, and no units along the z-axis. Since it's trig, well, let's just go and do everything in terms of trig units again. So we could try plugging in, say, pi over 4. So pi over 4 will give me cosine of pi over 4, about 0.7, sine of pi over 4, about 0.7, and then pi over 4, which is about 0.75. So we'd have a point, let's see, about 3/4 of the way over, about 3/4 of the way up, and then about 3/4 of the way up here when we would have this point. At h equals pi over 2, we would have cosine of pi over 2, which is 0, sine of pi over 2, which is 1, and z equals pi over 2, which is about 1.5. Pi is about 3. So we would then have, let's see, a point 0, 1, 1.5 up. The problem is it's really hard to get a sense of what these things look like right here. There's some kind of curviness happening between here, but how do you draw it and how do you understand it a little bit better? Mere mortals, it's hard for us to draw on R3, but one of the things that we can do is we can look at its projections. The idea of a projection is to look at this curve from either straight down, so that you only see the part in the xy plane, but you don't see the height, or straight down the x-axis, or straight down the y-axis. It's kind of like casting shadows along each one of the coordinate planes. So for example, we could look at the xy projection, and the basic idea of the xy projection is we're just going to ignore the z component right now. So if we were to look at this equation in the xy plane, we would say, all right, we have x is equal to the cosine of t, and y is equal to the sine of t. Well, we've seen that this thing right here traces a circle in the xy plane. What that tells me is that if I were to look down, straight down the z-axis from above, what I should expect to see is a circle moving around counterclockwise over and over and over again. So this is what I would see from this moving dot if I looked straight down the axis. What if we instead looked straight down the y-axis? So I'm not going to care what happens to the y component. There I'm just going to have the equations x equals the cosine of t and z equals t. Well, what kind of equation does this look like right here? Well, we've already got the second equation solved for t, so if I plug that into the top equation, we're going to get x is equal to cosine of z. So what that means is, if I were to treat z as the input variable and x as the output variable, I should expect to see a cosine curve moving right here. I should expect to see a cosine curve. And I could plug in a couple of values of t. When t is equal to 0, I get z equals 0, x is equal to cosine of 1. When t is equal to, say, pi over 2, I'm going to get pi over 2 cosine of 0, and so I'd get a shape who looks something like this. So what does that tell me? That tells me that if I was looking straight down the z-axis, I would expect to see the particle weaving its way up the z-axis in some kind of cosine fashion, because I'm going to see a cosine curve that's working its way up the z-axis. What if we were instead to look at the yz plane? In the yz plane, we're going to ignore the x value and only look at the y's and the z's. So there we're going to have the equation y equals the sine of t and z equals the cosine of t. Sorry, z equals t, my bad. And so if we solve this equation, we're going to get the curve y equals the sine of z. And so if I were to sort of make a quick sketch of that, with z being the input and y being the output, because that's how I know how to sketch the sine curve, I'm going to see a sine curve going up the z-axis. So if I were to try to, the idea here is if I was looking straight down the x-axis to the zy plane, then I would see a curve who's sort of meandering its way up the z-axis. Well, let's try to put my three motions together. I know that if I look straight down the z-axis, I'm going to see a point who's moving around and around and around and around and around and around the z-axis all of the time. But if I look at it straight down the y-axis, I'm going to see a point who isn't staying flat, but who's moving constantly up the z-axis. So put those two motions together. It's a point who's circling around the z-axis, but always moving its way up. And I might get something who looks like this. It would start here, and it would spiral its way around the z-axis, but constantly working its way up, higher and higher and higher. And if I were to sort of track this down backwards in time, then I would sort of expect to see this spiral going down. So what I would see is I would see a curve who's spiraling around the z-axis. Such a curve is called a helix. It can be really hard to draw these things in 3 dimensions, and so that's where computer technology comes in handy. If we use Maple to plot this curve, we get a graph that looks like this. But the cool thing about Maple is I can actually grab it and start to rotate it around. And so I definitely can get that sense of something spiraling around. If I were to look straight down the z-axis, then I see circles, just like we saw before. If I were to look down one of the axes, so this is straight down one of the axes, I see a sine curve. Whereas if I were to rotate this 90 degrees and look down the other axis, I would see that cosine curve. And so I do see that this helix, this spiral around the z-axis, does in fact have all of the properties we ascribed to it. Given the space curve r of t equals 2 cosine ti plus 2 sine of 2tj plus cosine of 2tk, plot its 3 coordinate projections. So in other words, those views we get when we stare straight down an axis. So let's plot its xy projection first. What we get if we ignored the z variable. So if we ignored the z variable, we'd only be focusing on the first 2 components of the vector. So x is equal to 2 times the cosine of t, and y is equal to the sine of 2t. So one of the best ways to at least start with this is to go and plot some points like we've been doing up to this point. Try to get a sense of what's going on here. So I will use 0, pi over 4, pi over 2, 3 pi over 4, and pi as my starting values. So we plug in 0 into our equations. We're going to get 2 times the cosine of 0 and the sine of 2 times 0. So our first point is going to be right here at 2, 0. At pi over 4, we're going to get 2 times the cosine of pi over 4. That's 2 times 0.7, or about 1.4. The y value is going to be the sine of twice pi over 4. That's the sine of pi over 2, which is 1. So we're going to get the point 1.41. At pi over 2, 2 times the cosine of pi over 2 would be 0. And the sine of twice pi over 2 is the sine of pi, which is also 0. So we get this point. At 3 pi over 4, twice the cosine of 3 pi over 4 will be in the negative quadrant, so we're going to get negative 1.4. And the sine of twice 3 pi over 4 is the sine of 3 pi over 2, which is minus 1. So we're going to get this point down here. And you can check that if we plot the remaining points, this point will get doubled in the middle. We'll get back to here, and then we'll double this point. And then we'll simply cycle these points over. And so we're going to get a curve who looks something... Whoa, I don't know where that word... And so we're going to get a curve who looks something like this, cycled over and over and over again. We're going to get an infinity curve. What about the other 2 projections? Let's take a look down the x-axis. So we're going to take the yz projection. So since we're staring down the barrel of the x-axis, we're only going to see these 2 components. Y equals the sine of 2t, and z equals the cosine of 2t. Well, this should look pretty familiar. We've seen equations who look like this. Sine of something, cosine of something. We saw in the previous examples those traced out circles. So let's just plot a couple of points just so we can get some sense as to what this circle is doing. So I'll do 0, pi over 4, pi over 2, 3 pi over 4, and then we'll run with it. So when we plug in 0 into this, we're going to get sine of 0, cosine of 0. When we plug in pi over 4, we're going to get sine of twice pi over 4. That's the sine of pi over 2, which is 1. and we're going to get cosine of pi over 2, which is 0. If we plug in pi over 2, we're going to get sine of 2 times pi over 2, which is 0. And we'll get the cosine of twice pi over 2. That's the cosine of pi, which is minus 1. So let's just plot these points. The first point we had y equals 0, z equals 1. Then we had y equals 1, z equals 0. Then we had y equals 0, z equals negative 1. And it's pretty clear that what we're tracing is a circle going clockwise of radius 1 in the yz plane. What about that last coordinate? What happens if we stare down the barrel of the y-axis? So we only see the xz plane. So in this case, we're only going to focus on the x and the z terms. So we're going to get x is equal to twice cosine of t, and z is equal to the cosine of 2t. Now if we plot a couple of points like we did last time, t, x, z, 0, pi over 4, pi over 2, 3 pi over 4. Let's see. We're going to get at 0, 2, 1. So we'll start at the point x equals 2, y equals, or z equals 1. When we get pi over 4, we're going to get twice the cosine of pi over 4, which is 1.4. And then we'll get the cosine of twice pi over 4. That's the cosine of pi over 2, which is 0. At pi over 2, we're going to get twice the cosine of pi over 2, which is 0. And then we're going to get cosine of twice pi over 2. That's the cosine of pi, which is minus 1. So we're going to get this point down here. At 3 pi over 4, we're going to get a negative 1.4 and a 0, sort of by symmetry. And then at pi, let's see, we're going to get twice cosine of pi, which is negative 2, and then the cosine of 2 pi, which is 1. So it looks like we're starting to trace some kind of an ellipse out here. But pay attention to what happens next. If we go to 5 pi over 4, the cosine of 5 pi over 4 is negative 1.4. Is negative 0.7 roughly, so twice is negative 1.4. And we plug in this point into the second one, we're going to get cosine of 5 pi over 2. The cosine of 5 pi over 2 is 0. So that puts me right back at this point. And in fact, if you plot these points, you're going to find that it goes back and forth, tracing out this little U shape over and over and over again. If you want to work out exactly what this U shape is, I'll just bust out a trig identity, what's known as the double angle formula for cosine. One of the double angle formulas for cosine is that the cosine of 2t is equal to 2 times the cosine of t squared minus 1. So if I get rid of this first equation, and just write this one here, I've got two equations, and I could go through the process of eliminating the variable. If I solve this first equation right here for t, I would get x over 2 is equal to the cosine of t. Well, actually, the second equation has cosine of t in it already, so I'll just plug it in and get z is equal to 2 times x over 2 squared minus 1. So z is equal to 2 times x squared over 4 minus 1, or z is equal to 1/2 x squared minus 1. So that's a parabola who's shifted 1 unit down and who's slightly wide. And that would be exactly this guy. What would happen if we tried to put these three pictures together? Could we? Imagine I were to have the z-axis pointing up and the x and y axes forming their plane at the bottom. What I see is I see a shape who, if I'm staring straight down the z-axis, is tracing out an infinity curve over and over and over again. That's what I see staring straight down. If I stare down the z-axis, I'm going to see a curve who starts up top, but who goes around in circles. Whereas if I look at it straight down the y-axis, I'm going to see something going back and forth like this. Back and forth, back and forth. Can you see how to put those motions together? Something who wraps the shape of an infinity curve from the top down is moving circularly along the zy plane, but is going back and forth in the xy plane. I'll admit that I'm having a hard time seeing something like this. The best bet that I can sort of think of is that it's an infinity curve, like a flat infinity curve like this, and then I'm going to bend it up so that it makes a U shape from the side. So imagine sort of making an infinity curve, but we're going to coil the infinity curve up so that it comes up something like this. And then we're going to take this thing and we're going to also loop this part up like that. Now again, My picture doesn't do this any justice, which is why technology rocks. If we were to render this curve using Maple, this is the plot we get. It doesn't look a thing like what I was describing it as just yet, but let's see if we can get some sense for it. If we were to go and look at this thing straight down from the top, so the view straight down the z-axis, then we see an infinity curve, just like we said. On the other hand, if we were to look straight down the y-axis, there's that parabola that we saw. And if we were to rotate it 90 degrees to look down the x-axis, there's the circle we saw. So as we move it around from different points of view, I guess that idea that I had was right. It is a figure 8 curve. It's just been folded up so that from the side it looks sort of U-shaped and from the front it looks round. But you notice that at any time I stop it, just even every single one of these individual frames, it's very, very hard to get a sense as to what a plane curve is unless you can grab it and rotate it around right here. If you think about it, that was a problem in Calc 1 too. It's very, very hard to get a good graph, a good sense of the graph of a curve by just plotting points. What we really needed was we needed calculus. And so that's what we're going to head to next.